I welcome you all for another session on mechanics of materials, module 1. Okay, module 1 is so big. We spend normally about 30 to 35% of the total time on module 1 because it is basically a fundamental one, and if you clearly understand module 1, then all other topics can be understood very easily. So therefore we normally spend, and don't mind to spend more time on this. And you also need to practice more, and so that you'll gain very good base, and you can understand very easily the other topics. Okay, I have listed out the content topics, what I intend to cover. Hooke's law. Okay, you have been talking Hooke's law probably from your second or third day onwards only, and still I bring Hooke's law. Okay, I don't want to go to the statement of Hooke's law. Okay, many of you probably are ready to say what is Hooke's law. Okay, I don't want that. What is Hooke's law? What does it do, or how does it help? What is the significance of Hooke's law? Hooke's law basically helps us to estimate what is the change in the dimension. Okay, so when I apply load on a body, you know that all bodies are flexible and they undergo deformation, the dimensions will change. What is the change in the dimension? So usually any change in mathematics, change means final minus initial. Change in dimension, it may be plus or it may be minus. I hope you understand what is meant by plus and minus. Okay, so Hooke's law helps us to find out, okay, what is the change in the dimension. That's all. Okay, so usually this Hooke's law talks about in only one direction, along the direction of the load or along the direction of the stress. What is it? If I have a member and I apply a tensile stress sigma, okay, and if E is the Young's modulus of elasticity, then sigma upon E is what is called as strain, or sigma upon epsilon is a constant within elastic limit. That is what is the meaning of Hooke's law. And what is epsilon? That is nothing but strain, that is nothing but change in length, change in dimension divided by the original dimension. So that is how Hooke's law helps us to find out the change in dimension. And as you know that all our bodies are three-dimensional, you have dimensions in all the directions, x, y, z direction. And in general, though we have started the load only along the one direction, along the length, if you call it as x-axis, right now we have only one load in only one direction. But later on, and it is only very primitive study, or what should I say, very introductory study. But all our bodies, in machine parts, they are all subjected to loads in all directions. If you call them as x, y, z, three dimensions, then along x-axis, y-axis, z-axis, we have loads and we have change in the dimensions in all the directions. If I use Hooke's law to calculate what is the change in the dimension in all the three directions, that's what I call it as Hooke's law extended to, or making it generalized. Okay, that also I have discussed, and by chance if you have a three-dimensional body, whatever may be the dimensions, and if I have this what I have discussed in my last class also, and if I have what is called as sigma x, sigma y, okay, sigma x and sigma y and sigma z, I am showing only three stresses in the three directions. Please remember that exactly opposite faces you have the equal amount of stresses, and if the body is made of a material whose Young's modulus of elasticity is E, then we have what is called as, we have strains in x direction, y direction and z direction. And if I have to calculate what is called as the strain in x direction, strain in y direction, strain in z direction. So what is the strain in x direction? Whatever is the change in the x direction. If I call this is my x-axis, say this is y-axis, and say this is z perpendicular to the board. Okay, so I have strains this epsilon x from the contribution of sigma x, sigma y and also sigma z. Okay, so epsilon x and sigma x, okay, the strain due to sigma x is longitudinal strain, and and the strain due to sigma y is lateral strain. The strain due to sigma z in x direction, that happens to be lateral strain, and therefore this is what we wrote using the Hooke's law. So epsilon x due to x sigma x, this is what is nothing but sigma x divided by E. Please remember, this is the strain, okay, along x-axis. This is longitudinal, and strain due to the sigma x in y direction, what is that? That happens to be a lateral strain, and this is minus mu into sigma x by E, and similarly this is minus mu into sigma x by E. So how did I write this? This is using purely Hooke's law. And how did I write this? Making use of the definition of Poisson's ratio. So what is the lateral strain due to sigma x in y direction? So using Poisson's ratio I have written, and similarly this term I have written it using Poisson's ratio. Okay, so please remember, all these strains are due to sigma x in different directions. Similarly, I have strains in x direction, y direction and z direction due to sigma y. Okay, so sigma y and y direction. Sigma y and y direction, what is that? They are like longitudinal direction. Sigma y and y. Therefore, sigma y longitudinal direction, sigma y upon E. The same thing, the strain due to sigma y in x direction and z direction, they are lateral direction. Therefore, this is minus mu into sigma y by E. This is minus mu into sigma y by E, and what is the symbol here? This is plus, because this is extension. These two are compression. If there is extension in the x direction, there is a compression, and in z direction also there is compression. Therefore, this. And similarly, on the same lines, without much explanation, I can write sigma z by E, and this is minus mu into sigma z by E minus mu y. Sorry, minus mu and minus mu into sigma z by E. Mu is Poisson's ratio. Okay, so this is what I call it as a generalized Hooke's law. The same thing I had told it in my previous video also. So why I am repeating it? Because I need to use these things in my further discussion. So this is very important. What did I do? Please remember, this also is Hooke's law. Hooke's law extended to all the three directions. This is what I mean by generalized Hooke's law. And I think you also have solved problems. If you have not yet solved, please solve problems. I have assumed sigma x, sigma y and sigma z as tensile stresses. Okay, and that is why I call them as positive. Any tensile stress I call it as positive, and sigma x, sigma y, sigma z, any one of them or all of them may be compressive also. In that case, you need to substitute that value, compressive stress, along with minus sign, and this is what you are supposed to calculate. And what is the significance of calculating this epsilon x, epsilon y, epsilon z? That also I have showed you. Epsilon v, what is this? Volumetric strain. This is the sum of all these strains. Epsilon x plus epsilon y plus epsilon z is what is equal to the volumetric strain. Okay, I hope you understand this. And this is not new, and this you already know, and I have revised it as I am going to use it again. Then what do you mean by a new term? What do you mean by state of stress? This is a way of asking what is the stress at this point. Okay, you have a body, and imagine that you have loads in all possible directions. Then you have chosen one particular point, and I want to know what is the stress at this point. So that is the meaning of a state of stress. What is the stress at this point? Is nothing but, in better words, in technical words, we call it as state of stress at a point. Okay, how do you express the state of stress? Okay, initially also once when I took very first class or something like, I had told you something what is called as a tensor. Okay, stress is not just vector, it is a tensor. What is the meaning of that? It has magnitude, it has direction, it has one more thing. What is that? That is the plane. If you are asked to calculate the stress at a point, anyone asks you, okay, it is a meaningless question. What is the stress at this point? For example, let me make it very clear. Very simple. Say a bar, a circular cross section, or it is subjected to a load. Say load P, say this is about say 10 km, and the cross sectional area, if I take a section like this and say is 100 millimeters square. Okay, I have a question. Say this is a point. What is this point? Point X. What is the stress at X? Okay, anyone asks you, find the stress at point X. Technically speaking, the question is not correct. So why? The stress at this point X, okay, depends upon how the plane passes through. Okay, most probably immediately you will take a plane like this. Okay, then the stress at this point is equal to load divided by 100 mm square, and therefore sigma is equal to 10 kilonewton divided by 100 millimeter square. Okay, that is how you may find out and you may answer. But who told that you have to take the plane like this? I did not tell you that the plane. Calculate the stress on this plane at this point by taking the plane like this, then your answer is right. I can take the plane like this also, or I can take the plane like this also, or I can take the plane in any other, okay, like this also, and find out the stress at the same point. Please remember, the stress at the same point can be expressed by taking plane passing through that point. In how many ways I can take the plane? Theoretically, I can take infinite number of ways, and therefore stress at a point can be expressed in infinite number of ways. Okay, how to express finally how the stress at a point is expressed? So what is normally done is, say you have a body, you have identified a point, that body is loaded, okay, and you have identified a point and you want to know what is the stress at a point. So what is the state of stress at that point? So what is normally done is, you imagine a small cube surrounding that point. Imagine a small cube surrounding that point. That cube, that point what you have identified now, that should be at the center of the cube. And the dimension of the cube are quite small. Okay, only one dimension is sufficient. It is a cube. Yes. Imagine a small cube surrounding that point. And how many faces are there? How many faces? It has 6 faces. And express the stress on all the 6 faces. That indicates what is called as state of stress. The state of stress at a point is expressed by imagining a small cube surrounding that point and stating the stresses acting on all the planes. In general, I believe that if I take a plane like this, then what all things I have? Do you want me to elaborate slightly? Say for example, this is the point, and say this is the plane how I am cutting it, and say these are the normal stresses. Take either this portion or this portion and draw the free body diagram. What does it look like? It looks like this. If I take the left hand side portion, this is P, and for the equilibrium of this, okay, this portion where you have cut, where you have taken section, this material deposited here at this section shall produce a internally developed force, and that force also, which I call it as say Pi, this also must be equal to P. Please remember, this Pi which is equal to P is not normal to this section, and therefore what I do is I resolve it. This what I call it as PL, the normal component, and this component which I call as the tangential component. So the tangential component divided by this area, not A. This area is more than A. Okay, A is the cross sectional area. If I take section here, that is A. Okay, this area is more. PT divided by this area will give us what is called as shear stress. The normal stress component, this Pm divided by this area will give us what is called as the normal stress. In general, on a plane we have both normal stress and also shear stress. As a special case, on some planes I have only one type of stress. Only either normal stress or only shear stress. Such states are called as what is meant by pure stress. Okay, if you take a plane and on that plane, if you have only one type of stress, either normal or only shear, then that stress is called as pure stress. Okay, only one type of stress. Or in general, if the plane is inclined, okay, in that case you have always what is called as both you have normal stress and also shear stress. Okay, so what is mean by state of stress? Okay, I want to find out the state of stress at a point. I imagine a cube. Okay, so this is the point. I imagine a cube. Okay, the cube imagine is very small, but if I draw that small, you won't be able to see it. I am making it slightly bigger, the cube. You have a cube like this. Okay, I shall show the point later on. The point is at the center, so this is the point. Okay, how many faces? This is one, what you see front. This is second, number 2, and exactly behind this, number 3, and one at the bottom, and one side, right hand side, and another one left hand side. Okay, you have 6 faces. Okay, so I would like to show a general one, general state of stress. What do you mean by general state of stress? General state of stress is nothing but 3 dimensions. Assuming that I have stresses in all the directions, x, y, z. 3-dimensional state of stress, that is called as. No, I don't have 3-dimensional, I have only 2-dimensional. So only along x and only along y I have stresses. Then that state of stress is called as 2-dimensional state of stress. And I don't have even that, I have only 1 dimension. Only along stresses along only one direction. In that case it is called as 1 dimension. So if you have like this, say if I have say sigma x here and sigma x here, then this is called as 1 dimensional. Okay, in the bar, whatever you have discussed or you are discussing in the first module, you have this kind, 1 dimensional. I don't have any stress along y axis or this thing. Now this is what is called as 1 dimensional state of stress. Okay, it is not 1 dimensional, it is 2 dimensional. Okay, I have sigma x and I also have what is called as sigma y, and the bottom here also sigma y, and there is no guarantee that I don't have shear stress. I may have shear stress here also. I may have shear stress along what is called as this, and I may have shear stress here also. I may have shear stress here also. I may have shear stress here also. So what are the magnitudes of these shear stresses and what are the directions, etc. That's what I am going to discuss very soon. That is what is meant by pure shear, how the directions are, the shear stresses, etc. What is meant by complementary shear, all that very soon I shall discuss. Okay, so I have, okay, this is called as usually the notation. This is the notation, this is, what is this? Shear stress tau. Okay. Shear stress acting on what? Acting on this plane. This plane, how is this plane? This plane is perpendicular to x-axis. This plane is perpendicular to x-axis, assuming that this is my x-axis, this is y-axis and this is z-axis. This plane is perpendicular to x-axis, I have one suffix. And acting in what direction? Acting in what direction? This is the shear stress. Okay, its toe, it is acting on a plane perpendicular to x-axis and acting in a direction what is called as y-axis. This I call it as tau xy. Every shear stress shall be indicated in state of stress with two suffixes. The first suffix shall indicate on what plane. Okay, so how is the plane? The plane is perpendicular to the first suffix, and the second suffix indicates the direction. And similarly, why not two suffixes for the normal stresses? So you can try and you will come to know that, okay, sigma, this is the normal stress. Okay, normal stress acting on a plane, and the plane is normal to what? The plane is normal to x-axis, the first suffix, and acting in what direction? It is x-axis. You will have sigma x. So instead of using sigma x, since both of the suffixes are same, and therefore we use only one suffix. And similarly here, sigma y, okay, this acting on a plane perpendicular to what? This plane is perpendicular to y-axis, sigma y. Acting in what direction? Y again, sigma y. Sigma y is same as sigma y. Okay, and therefore, okay, in two dimensional, you have sigma x, you have sigma y, you have what are called as tau xy on this face, and also on this face. Okay, so I shall show why not only these two faces. I shall prove that we can't have shear stress like that. Shear stress, if you have on this face, it has to be there on this face, it has to be there on this face, and also on the bottom. Very soon I shall show it. So many times two-dimensional state of stress is also represented like this. It is sigma x, and say this is sigma y, and say tau xy, something like this. This is how it is represented. The third dimension is not shown. That doesn't mean that it is not there. Z dimension is 0. No. The cube, it is having dimension in the third this thing also, but we don't have stresses in that direction. So therefore, many times two-dimensional, this diagram is simplified to this. Both of them are one and the same, and this exclusive study is made in module number 2. An elaborate study of this is made in module number 2. That we shall take up later on again. And the same thing, the extension, if you have the stresses on these faces also, in Z direction also, and then that is what is called as three-dimensional state of stress. Probably when I am discussing in module number 2, I shall draw that three-dimensional state of stress, then reduce it to two-dimensional state of stress, and then continue the analysis. So right now I don't need three-dimensional state of stress. Okay, therefore I shall not discuss it. But you should know what is state of stress. State of stress at a point is nothing but expressing the stress at a point. How does it done? So it is done or by imagining a cube surrounding the point and expressing the stresses on all the faces of the cube. That indicates what is the state of stress. So again, in how many ways, say I have a point here, I want to know what is the state of stress. Okay, I want to imagine a cube. In how many ways you can imagine the cube? In how many ways you can imagine a cube? I can imagine like this, of course the other dimensions. I can imagine the cube like this. You just tilt it and you have every time more different orientation, and therefore all these, how many ways are there? The stress at a point I can express it, okay, by imagining a cube. In how many ways I can imagine the cube? Infinite number of ways, and therefore the stress at a point can be imagined, expressed in infinite number of ways. Please remember, all those different ways express the stress at the same point, and therefore all of them are related. All the states of stresses expressed in different orientations, they are all one and the same. They all are related and what is that relation? That is the one what you are going to study in module number 2. Okay. So now let me continue further. Pure stress, and now pure stress, as you all know that on a plane, if we have only one type of stress, then that stress is called as pure stress. So I can have pure normal stress. That's what you are discussing in module number 1. Most of the problems you have only that. And now I want to discuss what is meant by pure shear. I have a case of pure shear. Okay, I imagine a simple situation like this. What is this? So I have a plate like thing. So you can imagine a duster like this. Okay, this is what it has, the other dimensions also. Okay, so this is one plate. And I have one more of this kind. Okay. Since I am going to join the two, and therefore I have just kept one above the other or one below the other. Okay, this is plate number 1. This is plate number 2. Remember like this. I want to join them. Okay, there are so many ways of joining, and what I do is I make a hole here in this plate. A true hole. Okay. And similarly, I shall make a hole here also, in this plate also, in the bottom one also. Okay, then I take a pin like this and insert here. Okay, so it may be rivet, it may be a nut bolt. Okay, so I join this and put a cap here and put a cap here. How do I do it? It doesn't matter. It's a rivet like. Okay, now what I do is I pull this side and I pull this plate this side. The load is a tensile load. Okay, so though there is small amount of this thing, what is it called as they are not collinear. There is a small gap here. Okay, as the thickness is very small, and that effect I am going to consider it some other time. And now you imagine that they are almost collinear. Okay, the effect of non-collinearity, that I shall take it separately. Okay, now if I try to pull it, I gradually increase this load, go on increasing this load, What is happening? Okay, this plate is being pulled this way, this plate is being pulled this way. Okay, this pin now. The pin is the crucial one. Okay, so you will continue the load till it breaks. Where do you think it will break? So concentrate this portion. Where is it? It is this portion. This is where it is going to break. Okay, so the pin becomes one portion belonging to the top one, and the pin belonging to the bottom portion becomes like this. This is where it is going to break. Okay, so how is the load with respect to, where is the section now? The section is here. This is the section. With respect to the load, this area, this section, how is it? It is tangential. The load is like this, apart from this. Okay, this is the portion of the plate, and this is what is being pulled here, and this is the plate, this is being pulled like this, and this portion where you have taken section, okay, this P is divided by the area of the pin, cross-sectional area of the pin. Okay, what is this? Of course, this is a stress. What type of stress? Is it normal or is it shear? So with respect to this area, this section, this load is tangential, and therefore this stress, what I have calculated, is what is called as shear stress, and this is called as tau. And this is a case of what is called as a single shear. Okay, this is said the pin is subjected to single shear, what we say. Okay, tau is equal to P divided by A. And a very common example, okay, and suppose I have a plate like this and another plate like this and I have another plate, 3 plates, and all these 3 have been joined, say. So I pull this plate, this is one plate. I pull it this side. Okay, if this is the only load, then it is not a problem. The whole unit will start moving in this direction. Okay, this is not allowed to move, and by pulling it this side also, please remember it is not hollow. This side is also one plate, and this is another plate. So how much force you are going to apply? If you apply P and P here, it is not in equilibrium state. P and P, 2P is left side, P right side, and the whole unit will start moving in this direction. So therefore this is not P, it is P by 2, this also is P by 2. Okay, now the whole unit remains here only. Now this is being pulled this side, and these 2 plates are being pulled this side. Okay, the pin remains there only, and this load is continuing to increase till it fails. Assuming that this material across this pin is homogeneously strong, equally strong. If it is equally strong, then it breaks simultaneously at this point, at this juncture, and also at this juncture. This plate will break it at this section, and similarly this bottom one will break it at this section. Simultaneously the breaking, or it is subjected to that severity at 2 sections, and therefore, okay, so what is the load? Load is P divided by A, or P by 2 divided by A. If you take this P, then you will be taking this 2 area. If I take only this portion, in that case P by 2 divided by area. Okay, the tau is equal to, there are 2 ways of calculating, P by 2 area, or if you take this portion, it is again P by 2 area. If you take this P, then you have to take this entire portion. If you have this pin and this entire thing, and take here. Okay, this P divided by A plus A, 2A, or this is what is called as, this is the shear stress, and this pin is subjected to, we say that it is subjected to double shears. Okay, so looking at the diagram or how the loading is done, we normally say pin is subjected to single shear, pin is subjected to double shear. So I understand it is only an introductory class to introduce you to shear stress, and telling all this, you may not, I am not very sure whether you have understood or not, but subsequently when we take up problems, we will be definitely able to do that. I thought I'll be able to cover something more, and right now I shall stop it. So still these topics are pending, and I shall introduce what is meant by a case of pure shear, state of pure shear, and complementary shear, etc. That I shall explain it in my next class. It's 30-35 minutes.